We are delighted to have you all here during the Pi Day celebrations. Today, we are joined by Professor Ravi Kulkarni, who is a distinguished professor at Bhaskaracharya Pratishthan, Pune. He was former director of Harish Chandra Research Institute and mathematics chair at IIT Bombay. He is famous for his works in differential geometry, especially for the Kulkarni-Nomizu product. I am sure all of you would have seen a lot of definitions in mathematics. However, have you ever wondered about the definition of mathematics? Today, Professor Ravi Kulkarni will try to explore this deep philosophical question and arrive at a definition of mathematics. So sit back in your chairs and enjoy this talk, which tries to address the age-old question about the meaning of mathematics. We welcome you on the stage, sir.
For this invitation by the Math Club at IISER. Many of you may not know that I am associated with IISER from its inception. I used to be here several times in a year in the beginning years. And even now I come for some math seminars, etc. So, today I wish to address this question. Let me tell you the table of contents. Introduction, here I introduce the question, what is mathematics, and definition of mathematics, and say that this is a different type of question than the question that you have seen. Then I give you 3 quotes of some well-known mathematicians or physicists, what they think of mathematics. Now I discuss this one major example, that's by Newton's Principia. Then I discuss the issue of scientific methodology. The first issue is defining basic terms and what are the ingredients of a rational discourse. Then these epistemology and ontology, these are the words used in philosophy, and people in the sciences do not know these terms or have not used these terms, and the way the terms are used are in philosophy, they are rather broad. But here I shall make the precise meaning in our context of the epistemology and ontology. And then I shall tell you epistemology and ontology of the type of mathematics that we do. Then I give you a definition of mathematics. And the last topic is a well-known philosophical issue about mathematics, whether the mathematics is objective or subjective. Let's start. So you are all bright students here in your exams at IISER. I am sure you have written definitions of notions like groups, rings, fields, topology, measure space, etc. Now consider the question, define mathematics. This question will not appear in your exams because it doesn't have one clear answer. But it is asked in some higher level appointments, such as professorships or department chairmanships or institute directorships and so on, just to see how broad or deep the person is. I am sure this question has bothered a good percentage of your teachers from time to time. It has bothered me for the last 50 years. This is a very different type of question. I would call it a philosophical question. The answer is not carved in stone. A better formulation would be what Dedekind said about real numbers. Not that what is the definition of mathematics is not the correct question, but what should be a definition of mathematics? This is the question, and let's try to arrive at some consensus. Well, whatever mathematics is, we all know it's very pervasive. First, let us understand what is philosophy. You know, animals act by instinct, but humans do much more. they muse about their lives, who am I, where I am going, etc., and what is this world that I see and experience, when did it begin. Now, my dog expresses his love by licking my face, but I would rather use words to express my love, etc. So, I will use my language. So, highly developed language, music and mathematics are unique to humans among all animals. Using such devices, humans have created knowledge traditions. The word philosophy is used for the sum total of these knowledge traditions. It is a cumulative product of our past, useful for understanding the present and doing speculations about the future. And some of the brightest minds among us have a philosophical side to their personality. Philosophy is broadly divided into two categories. Natural philosophy, dealing with matter, the inanimate part of the world, and philosophy of the mind, dealing with the animate, living, conscious part of the world. We know mathematics has been a very important part of philosophy. So far we associate it mainly with the philosophy of, the natural philosophy of matter, but it could also be used about the philosophy of the mind. So, Newton called his magnum opus Principia, and the subtitle was The Mathematical Principles of Natural Philosophy. What Newton called natural philosophy, more precisely, we shall now call simply Newton's theory of gravitation in physics. What he called mathematical principles, more precisely, we shall now call just calculus and the theory of ordinary and partial differential equations. The word mathematics was already used there. It means that the word mathematics stands for certain ways of thinking or thought categories. So, asking for a definition of mathematics amounts to asking for a description of the nature of these thought categories, if possible in a succinct and simple language. If we are successful in answering the question of the definition of mathematics, it will be helpful in answering similar questions like definition of physics, definition of chemistry, definition of biology, etc. Let me know how many physicists are here, how many biologists, chemists. So you please ask these questions now, or at least know what is involved in this. So what we have before us as a data are the great scientific theories, these four scientific theories: Newtonian mechanics, electricity, magnetism, Einstein's relativity, and quantum mechanics. These theories have been formulated. If you see some original papers, you will see they've tried to formulate their theories on the model of Euclidean geometry. They start with definitions of certain key terms, the axioms relating them, and the subsequent deductions. Theory is always presented in a deductive form. There are issues about this presentation and the actual learning of the theory, but that's a different thing. As I am trying to say, the process of how to form definitions, axioms, and the methodology of deductions are philosophical issues. These were the concerns of the Aristotelian logic in the Greek-Roman knowledge system and the Nyaya Darshan in Indian knowledge system. When I was in college in Pune, I guess 60 years ago, at that time, one of our really very good professor, we had a course in logic, and that was mainly Aristotelian logic. He mentioned some Nyaya Darshan and he knew it, but somehow those were not the topics of discussion at those times. But the Nyaya Darshan is still not very much discussed, but I think it is very relevant to what I am talking today. I know now this is, as some of the teachers here may know, the Indian knowledge system is emerging as a new discipline. Ancient Indian mathematics and astronomy are a very important part of IKS, and here my friend Professor Katre is one of the experts in this area. IKS comes into two parts. IKS means Indian knowledge system, theoretical and applied. Mathematics and astronomy are on the theoretical side. Along with them, there are also darshans. We call them darshans, you can call it just philosophies. On the theoretical, this is also theoretical side, like Sankhya, Vaisheshik, Yoga, Nyaya, Vedanta, Mimamsa, and also other part, Buddhism, Jainism, Charvak, etc. These are all called darshans. An interesting point, a very large part of these darshans in the IKS has nothing to do with the fact that they are part of the Indian knowledge system. There is nothing Indian about them. They are like sciences, physics, chemistry, psychology, mathematics. That's the way they should be viewed. And mathematics really plays an important role in these philosophies. In addition, it of course plays role in all the applied parts of IKS, like medicine, music, engineering, metallurgy, etc. So these are universal parts. So in my lecture, I shall mainly restrict to the topic of the definition of mathematics, but I wish to put this IKS direction for consideration before the mathematical community. I especially wish to thank Kailash here for helping me with the presentation here. I am learning these things. Now let me start with three quotes. Andre Way, how many of you know Andre Way? He was a great mathematician of the 20th century, and he was also kind of very philosophical mind. So people used to tease him or ask him, what is mathematics? What is mathematics? So this is the thing which I heard. I've seen the man in 1980s and 90s. So he just used to say mathematics is what mathematicians do. Now, is this a definition of mathematics? Now, this expression compares favorably with two statements about real numbers found in actual texts of elementary calculus. First statement, real numbers consist of rational numbers and irrational numbers. And secondly, what is irrational numbers? They are real numbers which are not rational numbers. My question, are we defining real numbers here? We are not talking complete nonsense. We are saying something meaningful. You formulate these statements in terms of sets. So we are saying that the real set of real numbers is a union of two of its subsets. The subset of rational numbers and subset of irrational numbers. And the second statement clarifies that the union is disjoint. That is, the intersection of the subset of rational numbers and the subset of irrational numbers is empty. Now I ask you a side question. Can we replace the subset here by set? Can we say that the intersection of the set of rational numbers and the set of irrational numbers empty? So that will test how much you understand the set theory. These statements express a certain feeling of the mathematical community about real numbers. It presupposes, of course, that we absolutely know what the rational numbers are, and real numbers form some superset of rational numbers, and we know that this superset contains some numbers like root 2, root 3, which are irrational. Now, etymologically, positive rational numbers are those numbers which can be expressed as ratios of two natural numbers. And so, etymologically, irrational numbers are those numbers which are not such ratios. So that is the main feeling. But when we wish to develop a theory, the main issue is we need to clarify what are the numbers. We use the word numbers. What are numbers in the first place? And then what are the irrational numbers? And ideally we should know this whole set of irrational numbers. If that is so, then that would be a reasonable definition of real numbers. So these are some of the issues. Now you can understand what kind of issue, what is mathematics is. Now second quote by the great Einstein. Here is what Einstein says about mathematics. Roughly we know he was biased towards physics, and more bluntly he would have said physics deals with reality, mathematics doesn't. But the original quote is more nuanced. He says, as far as the laws of mathematics refer to reality, they are not certain. And so far they are certain, they do not refer to reality. You may have heard this statement. Despite the fact that the statement is coming from a great iconic figure in science, I find the actual statement quite confusing. For what he means by the laws of mathematics, what he means by reality, and what he means by certain is not at all clear. Again, we can ask, what are the definitions? So, do the laws of mathematics contain real numbers as a very important part? If so, is he calling the real numbers real, but not certain, or certain and not real? Or is some combination of reality and certainty about them? As for Einstein's fame as a scientist, he was the first to associate light signals with time. This was the completely new element in the physics of his times. And a la Newton, time was always mathematically modeled on real numbers. Time is a physical concept, is a physical experience. We model it, or Newton also modeled it over real numbers. So, knowing that the speed of light was large but finite, Einstein knew this fact. This was proved before. This was experimentally proved before. So, Einstein intuitively surmised that this finiteness would violate Newton's postulate. Newton's first postulate is axiom, space and time are independent. And Einstein somehow realized that the finiteness of the speed of light, if you associate that with time, then these two statements do not match well. Now, what he did with this intelligent guess, is it mathematics or physics? I leave it to you. I would say that at least what he did, what in our community, what in the mathematical community we call mathematics. Minkowski considerably improved on his presentation. Now, as for the third flippant possibility, as a possible definition of mathematics, let me take all mathematics that is taught in the departments of mathematics all over the world. What is this definition? With this definition, mathematics becomes time dependent. For what I learnt as mathematics when I went to college is widely different from what you learn now. And also this definition is just too vast. It will take a few pages to write it down in detail. These issues are considered in Nyaya Darshan, by the way. A theoretically tenable good definition should be very succinct. Sankshipta akshara komala amalapada. These are the words of Bhaskaracharya at the beginning of Lilavati. So mathematics should be, he is saying it should be beautiful, it should express the larger thought in a succinct way. Anyway, this third variant is just Andre Wei's, is a variant of Andre Wei's jocular definition. The definition does not serve any purpose in explaining the nature of mathematics. So, what is clear from these statements, from these attempts, is that there is a kind of human activity that is recognized as a mathematical activity by a large part of humanity throughout its history. One needs to look at the instances of human experience of what was and is considered as mathematics and come up with a definition that will cover these instances and which will be a tool to classify any new instances, whether we are doing mathematical activity or not. What we are concerned about mathematics, our friends in physics, chemistry, biology departments are similarly concerned or should be similarly concerned with their disciplines. It is not possible to answer the question about definition of mathematics within the domain of mathematics. We have to go outside mathematics for this. Historically, such questions were named philosophical questions. I have said this before. So, many of your teachers have worried about such questions in their life, and I wish to tell you in this lecture what I have been thinking in these recent years, in the last 10-15 years about such questions. I think every intellectual endeavor of humanity be considered as a theory about some domain of experience of humanity. Let us apply the criteria of scientific methodology which have been applied to scientific theories. I mentioned the 4 scientific theories which are developed in the last 4 centuries. So, these major scientific theories are Newtonian mechanics, etc. So, some of you may have seen this book by Thomas Kuhn, The Structure of Scientific Revolutions. This book refines classical Baconian view that the scientific progress is cumulative. Roger Bacon was, I think, a 13th century English philosopher. He understood the importance of science, and I forget the name of his book, and he thinks that science is cumulative, that is, the new facts just pile up. Kuhn popularized the phrase paradigm shift. This also phrase you may have heard, to explain the revolutionary changes brought about, for example, by Newtonian mechanics in the explanation of the astronomical data accumulated from antiquity, or the revolutionary changes brought about by Einsteinian relativity in combining space with time and mass with energy in Newtonian mechanics. I would say that in the language of this lecture, a paradigm shift can be explained just in terms of a major change of ontology of a theory, and in terms of the specific role that mathematics has played in the formulation of these theories of matter. Since Kuhn mostly dealt with theories of matter, there is a tacit Cartesian assumption, Cartesian is Descartes, that science deals with objective phenomena. That is, it is independent of the human mind. This assumption basically arises because of the use of mathematics in these theories and the apparent objectivity of numbers. We think 1, 2, 3, 4, this number system is really objective, outside human personality. And Kronecker was a 19th century mathematician, number theorist. You may have heard his famous quote, "God made the integers, everything else made by man." Of course, man is something we know, but what God is, he does not explain, he just says it. He was kind of responding to Dedekind's famous statement, real numbers are the creations of human mind. This is a very famous statement in the history of mathematics. His original paper is mathematics, but this statement is, from the philosophical point of view, is always quoted. Real numbers are the creations of human mind. And the title of his paper is, the point is not what are the real numbers, but what should be the real numbers. That is the title. I just leave it at that. Moreover, now we recognize space. Besides numbers, space is also a category of mathematical thought. If you consider the historical development, in my opinion, even the number category is not objective, and the space category is much less so. I shall say more about that in the last section. So, before going further, let me consider this very major example. One masterpiece of modern science is Newton's Principia, or the mathematical principles of natural philosophy. Its structure may be described as follows. In Newton's time, as I said before, natural philosophy was used for both physics and chemistry. You know, Newton was also interested in alchemy, which is part of chemistry. The book opens with some intuitive physical notions like space, time, place, mass, motion, etc. To these terms, Newton associated certain numbers. This is the part of formulation of natural philosophy using the mathematical principles. Finally, in terms of these numbers, the relationships of the terms is formulated as certain axioms, culminating in a precise law of gravitation, which all of you know, m1 m2 divided by d square. Now, this part 3 led to some differential equations, and when applied to the problem of two bodies, these equations can be explicitly solved. I am sure that you have been exposed to this solution. With such succinct formulation, vast amount of data, including the data about the motion of the moon around the earth and the motion of the then known 6 planets around the sun, painstakingly accumulated by the astronomers from ancient times, and much more was explained. This included Kepler's 3 laws of planetary motion. Moreover, the gravitational law itself was verified in many special cases, and it's still being checked for its accuracy, just to maintain that the same law still prevails. This is one of the work some of the major institutions in the world do. Newton's Principia, since its writing, has remained a model for any theory building in any intellectual endeavor of mankind. Now, a very important point, Newton's theory itself does not say that it is ultimate or absolute. Theory doesn't say it. People may start saying that. It allows for the possibility that a better theory may be found. If it is found, the original theory may be replaced by the new theory. So, in the 19th century, it was considered as a last theory about nature, but a better theory, Einstein's relativity, replaced Newtonian mechanics in the 20th century. Kuhn described this changeover from Newtonian mechanics to Einstein's relativity as a paradigm shift. Now, in scientific methodology, I say some of the salient features about this. A very basic part of scientific methodology is that in any given discourse, one should define the basic terms which are used in the discourse. This may appear to be so obvious that it need not be mentioned, but not so. There are certain questions about what constitutes a definition and what are the types of definitions. In fact, the Nyaya Darshan discusses many such issues. In the above major example, the first chapter of Newton's masterpiece is called definitions. The second chapter is called axioms. He is clear that some initial terms must remain undefined. There he does not offer the definition. He frankly says, I do not define what is space, what is time, what is place. Place means just part of the Euclidean free space. What is mass, what is motion. These are undefined terms. After 4 centuries, and today's scientific methodology would use set theoretic foundation to express these notions. And what is our today's interpretation of epistemology and ontology of a theory to formulate Newton's original theory. Now, science is truly a community effort with its own methodology. Just as no scientific theory is absolute, there is no single messenger. There are many messengers, but the message is more important than any of them. Now, it is instructive to contrast this age-old tradition in the history of science with the tradition set in the history of religions. In the history of religions, people are having debates, including fights, for centuries. Because the main thing is, in the discourse, they never start with the basic terms like religion, dharma, laws, God. They are never defined. And people start discussing and see the mess. Perhaps the mathematicians and scientists should help them. Now, another ingredient of the scientific methodology, these words are always used, that scientists are considering every discourse as a theory. And in the historical examples of the scientific theories, they have consistently looked for a rational explanation. You probably know the story of what Lagrange. He was a general in Napoleon's army. Lagrange wrote this famous book on, he reformulated Newton's theory in dynamic terms. And he presented the book to Napoleon, and probably Napoleon slept on that for 1 or 2 days, and he asked him, I don't see any God in your theory. So Laplace answered, I don't need that as a hypothesis in my theory. It is immaterial whether I believe in God or not. In a personal way, that is different. In the theory, that is not a hypothesis. So this is the viewpoint that our discussion, the scientific theories, that's a rational discourse, not appealing to any transcendental notion. And in the parlance of Indian knowledge system, the same issue is extensively discussed in Nyaya Darshan, and it is called Pramanya Vichar. A pramana means a method of proof. Every darshan in the Indian knowledge system at the beginning clarifies the pramanas it is going to accept. And you would be surprised that even Sankhya, Vaisheshik, these are kind of scientific darshanas, and they don't mention God anywhere. Or even Mimamsa doesn't mention any God anywhere in these theories. The 3 main pramanas accepted in IKS are the sense perception, which is called Pratyaksha Pramana, inference, and the Shabda Pramana, or an expert opinion. Now, in scientific theories, only inference is accepted as a pramana, not Pratyaksha or Shabda. You know, in mathematics, a picture is not accepted as a proof. Whether picture is used as to explain the proof and for understanding the proof, that is okay. But in the formulation, picture is not a proof. Editors of math journals would ask you to render a graph, not a picture, like some dots and edges, but they would insist, at least in math journals, they would insist that you should express that as vertex set and edge set and the relationship between them. And that is how it is formulated also on a computer. Computer doesn't understand pictures. I guess maybe for computer uses, no, but it is independent of the computer uses. Basically, a theoretical development, in a theoretical development, sense perception or pratyaksha is not accepted as a pramana. However, it is not difficult to see that in general, a sense perception can be reformulated as an inference. I don't go into this, but just as a picture of a graph can be reformulated as a pair v comma e, etc. Moreover, the issues with Shabda Pramana in IKS, it is used in yoga and Vedanta and at many places at IKS. But if you see the original sources, it's not some credulous thing that I'm believing in the Vedas, something like that, or I'm believing in the Upanishads, not like that. But it is used as an ontological statement for proof of certain statements. If someone is interested, I shall explain that further. Now, let me explain the role of inference. Every theory, scientific or not, arises as an explanation of certain data from a certain domain of human experience. The same data may be explainable by two radically different theories. The same theory may explain some other data different from the data which gave rise to it. All these possibilities have actually occurred in the history of science. A pervasive and beautiful example is the use of abstract theory of differential equations and partial differential equations in mathematics, which is constantly used in physically quite different theories such as Newtonian mechanics, electricity, magnetism, etc. Now, I come to the definition of epistemology of a theory. In any case, a theory is for communication between two individuals or two groups of individuals. So, it becomes imperative to decide when a certain statement of a theory is considered as proved, and people have to agree that yes, I agree, accept that as a proof. The two parties have to agree on such a decision. If a statement B is inferred from a statement A, then symbolically one writes A implies B. In Nyaya terminology, A is Karana and B is a Karya. It is readily agreed that if A implies B and B implies C, then A implies C. For two parties to agree on a theory, it is imperative that they need to agree on the set of all relevant statements and the possible implications between the statements. This is simply called the epistemology of a theory. The original use of epistemology in philosophy is too broad. I am just using the word epistemology of a theory in this precise sense. It is just the logic that is used in the theory. For developing a theory, now let me give an example. One needs more structure on its epistemology. For example, a large part of mathematics follows so-called binary logic. I think when we teach mathematics, we don't say that we are doing something philosophically, something significant, but we just tell you the rules. In this logic, every statement A has exactly one opposite statement denoted by minus A. Every statement, any statement in the mathematical theory, for the most part of mathematics, has to be either true or false, but not both. Otherwise, that statement is not part of the theory. Here the word truth, and it has exactly two truth values, namely we use the words true and false. But here the word truth is not in the sense of some religious conviction. It is a mathematical notion. You may simply write 0 and 1 for them, and with the only understanding 0 is not equal to 1. That is why it is called binary logic. This is perhaps the simplest kind of logic. It is very crisp, its decision making is unambiguous. The situations in science and more generally in life may have many more nuances. Mathematics with its binary logic is sufficient for the first three theories, major theories of science I mentioned above. I think it's not quite clear whether that will be sufficient for quantum mechanics. More generally in life, for example, in the office of a medical doctor or in a court of law, while binary logic remains a desirable goal, the actual judgments are reached after many adjustments, and different doctors or judges can make quite different judgments. Now, in mathematics itself, there has been a ternary logic. What we use is binary logic, but there has been a ternary logic. There is a logic with which has 4 values, and there is also this fuzzy logic called, it uses the set of values to be any subinterval of 0, 1. So, these different types of logics have been suggested even in mathematics. Now, I come to the ontology of a theory. Given the epistemology, if we wish to prove a statement B, it suffices to find a statement A which has been proved and such that A implies B. If A is proved and A implies B is true, then we accept B is proved. But what if A is not proved? So, reiterating the step, if we find a statement A1 which has been proved, and if A1 implies A, then A is proved, and so on. But such reasoning may lead to a defect called infinite regression. A theory must avoid infinite regression. This is precisely the point where Newton is saying, in my theory, I am not going to define space, time, place, mass, motion. He is saying that these are intuitively obvious or whatever. So, a theory must contain some initial statements whose proof cannot be questioned. And that is that I call the ontology of a theory. Now, in change from Newton to Einstein, Einstein changed this ontology. He related time with light signals. Now, let us consider mathematics itself as a theory. For the most part, like what you study at IISER, mathematics uses binary logic. So, we can, for this part of mathematics, we can take binary logic as the epistemology. What is its ontology? Up to the latter half of the 19th century, it was believed that everything mathematically significant can be finally expressed in terms of numbers. The system of natural numbers was the first abstraction suggested by the counting process. Now, if you watch a child, it can easily learn 1 and 2. But it takes a time. It has to be taught the numbers 3, 4, 5, etc. But with this teaching, a child goes way ahead of cats and dogs in a few years. So, what I am trying to say that this is a human activity. The counting process also suggested the binary operation of addition, and the binary operation of multiplication was readily derived from it. And the counting process also suggested that there are infinitely many natural numbers. For given a natural number and adding 1 to it, one gets a bigger number. And this was the first infinity encountered in a theoretical development arising from the counting process. You know, in Aristotle, there are discussions, is infinity a number? and he says infinity is not an even number. If with Aristotle, a number should be either even or odd. He says if it is an even number, I add 1 to that and it still remains infinite, but it does not become odd. that is the kind of reasoning in Aristotle. The same issue is discussed in Galileo. Galileo, some of the philosophical books are very interesting. I think you should have at least browse through them. So, what is infinity was one of the major issues in this theoretical development. So, anyway, but that infinity as a concept was understood now in this case, and adjoining 0, adjoining negative numbers, adjoining the multiplicative inverses of non-zero numbers, etc., and extending the binary operations to them, these two binary operations of addition and multiplication, these were the next major steps. Now, the next thing is that the numbers constructed so far could also be considered as lengths of line segments. So, after making some choices, these numbers could be assigned to some points on a long line. And now the converse question, given a point on a long line, is there a number corresponding to that? Now, any point on a long line could be assigned a number represented as a possibly infinite decimal. This is how Newton or Euler probably thought of real numbers. They did not define real numbers, but they thought of real numbers as some infinite decimals. Descartes' coordinatization process showed how a point in three-dimensional physical space of human experience could be described by triple of real numbers. Now, set theoretic understanding of the real line as an ordered set that is complete in the sense of Dedekind, and the real numbers as a complete Archimedean field brought space and numbers aspects together. This is due to Dedekind as late as 1879. This connection of space and numbers led to rich development in mathematics, in number theory, arithmetic geometry, algebraic geometry, analytic geometry, etc. So, whenever you write an equation in say 4 variables, you consider that not equation, but the left hand side of that as a function of these 4 variables, and we consider the corresponding level set as some subset of the Euclidean, I don't know, 6, 7 dimensional space. And how, so that's the space part. So, this is why we associated numbers with space, and conversely how far that process is complete, corresponding to a subset of a Rn. Can we describe that in some way in the number category? So, this was the major development that occurred in the 20th century mathematics. Now, these days we question natural numbers, integers, rational numbers are considered as arithmetic questions, whereas those related to real and complex numbers are considered analytic questions. These words are really flexible. Galois did not use the word algebraic, Galois used the word analytic. So, this is how the changes occur over at least centuries on mathematics. And now, the epsilon delta definition of continuity that you learn in starting calculus, this is due to Weierstrass as late as some 1870 or so. And that was hailed as a satisfactory arithmetization of analysis, and in this analysis he considered this space also. Before this definition, the continuity was surely intuitively understood by mathematicians through several examples, but there was no formal rigorous definition that could satisfy an inquiring students. But Riemann before Weierstrass, faced with the similar problem of defining continuity of a complex valued function of a complex variable, had just said a function is continuous if 2 points are close in the domain, then their images are close in the range. The word to be marked here close, he does not say what close is, but that is the beginning of topology, where the numbers are not used. Riemann did not have a proper language of topology. To define topology, one needs the language of sets to start with. So, sets were not in the picture. Everything was expressed in terms of numbers. The language of sets and structures on sets brought about a revolution in mathematics in the 20th century. So, using Kuhn's words, you can say that set theory gave a new ontology to mathematics, and it was a really paradigm shift in mathematics. If we change the epistemology or ontology, that would of course be a different theory. In our case, it will be a different description of mathematics. For example, we keep the same binary logic as the epistemology, but change the ontology from sets, the functions between sets and structures on sets, to, you may have heard, categories and functors. You see, there is a category of sets, but category is not a set. The main difference is set has a cardinality, whereas category does not have a cardinality. And it makes sense of some questions about automorphisms, etc. That is why the theory of categories came about. And also the set of all sets has no meaning, as Russell had pointed out. So, these are the theoretical difficulties in developing mathematics. So, similarly, if we use Kleene's three-valued logic or Zadeh's fuzzy logic, we are changing the epistemology of mathematics formulated as a theory. In the discussion of ontology of a theory, we have glossed over one subtle point, namely the meaning of the ontological word or statement. We just said that some of these statements have to be accepted without definition. But what is their meaning? At this point enter human mind and the whole issue of consciousness. Meaning is assigned only by human mind. Let us explain it in the major example by Newton. We have seen Newton's statement, I do not define space, time, place, mass in my theory. We have now interpreted space, time, etc. as ontological terms in his theory. Question is, what do they mean? By space, Newton probably meant three-dimensional Euclidean space of physical experience, Euclidean three-dimensional space of human experience. You can legitimately ask, what is E3? What is the Euclidean three-dimensional space? Please define it for me. Well, it is a three-dimensional affine space over the real numbers, where origin is chosen, so that it becomes a three-dimensional vector space over the real numbers. Moreover, it is coordinatized by Cartesian coordinates x, y, z, where the distance between the 2 points x1, y1, z1 and x2, y2, z2 is given by the Pythagorean formula. With this, now Newton has this in mind when he uses the word space. Similarly, time is a physical experience, but in terms of whatever years, minutes, whatever, this is meaning is given by modeling it over real numbers. Real numbers are just in mathematics. Newton is giving meaning to the word motion of a particle. He says, I am not going to define motion, but what he actually does he defines the path of a particle, that is a function from the time interval to the Euclidean 3 space, that is the motion. Now we define instantaneous acceleration. I believe in Newton was the one who introduced acceleration in science in the first place. Before that, Galileo had talked about velocity, but acceleration came with Newton, and he just takes it as the second derivative of this function. And so Newton uses the word mass. I have been slightly incorrect in giving these some statements here. Newton uses the word mass. Now, these two bottles have the same mass, do they? These masses are different. What do you mean they have the same mass? Mean they have the same weight. What is weight? Is a real valued, positive real valued function on the set of these objects. So, that is, and in the Newton's gravitational formula, when he uses the word product of two masses, he doesn't mean this physical notion of mass, he means these numbers in that gravitational formula. Then he would define force, that's the definition, mass times acceleration. And finally, the law of gravitation, which is a thoroughly inductive step. Newton is giving meaning to the ontology he had chosen using the number and space categories of mathematical thought. This is what he calls the mathematical principles of his theory. Similarly, in scientific theories, the SI units, Système International, so the length, mass, time, electric charge, temperature, amount of a substance, what you call mole, these are actually, say, you can call them physical concepts. But how do we use them in our equations? By giving appropriate real number valued functions on this set of objects. So, giving these meanings, use the thought categories of number and space. So, I suggest as a final definition of mathematics, mathematics is a theory with its epistemology and ontology, explaining some domain of human experience, where the ontological statements are given meaning using the thought categories of number and space. I would like to have comments of many of my colleagues here on this definition. This formulation probably clarifies the role mathematics has played in the development of scientific theories, and how and why a physicist like Eugene Wigner wondered about unreasonable effectiveness of mathematics in the natural sciences. So, he asked, well, atoms are here, something is happening here, but I am doing something on paper and this is mathematics, and why does it, some reality here correspond to that reality? Those are his questions, and he calls that this is unreasonable. Mathematics is unreasonably effective in natural sciences. But I think mathematics has been quite reasonably effective, not only in natural sciences like physics and chemistry, but also in biology, psychology, where mind starts playing a major role, and also in social sciences like economics, sociology, politics, and you are all exposed these notions already in physics, chemistry, as well as psychology and so on. And so, with this viewpoint, we can also look at the Indian knowledge system and find its large universal scientific part and build its bridges with the modern world. Now, the last point, this is a philosophical question about mathematics. Is mathematics subjective or objective? So, Einstein's like quotes on mathematical laws, reality, certainty make us mathematicians nervous, as if we are living in our own ivory tower world, built by our own minds, creating our own problems, which nobody else cares about. The problem about such quotes is that the basic terms are never defined. On the other hand, the governments all over the world today are trying to recommend their citizens to learn more and more mathematics, so that these citizens become better citizens and solve their problems in a rational manner without indulging in fights. So, this already answers that after all said and done, mathematicians are not ivory tower people. As for Einstein, I already said that it does not matter what he calls himself, but a good part of his work is what the mathematical community would call mathematics. One does not need to have a position in a mathematics department to do mathematics. I give you three wonderful examples here. Bravais, some of you in chemistry, you may have known about Bravais lattices, and in mathematics it comes as the crystallographic groups. So, he was actually, I saw on Google that he was actually a co-student with Galois in École Polytechnique, and he actually classified his work is classifying 230 crystallographic groups. He of course did not have the terminology of groups, but he observed that these are these 230 objects of molecular symmetries. He was a chemist. Around the same time, Galois was developing group theory. This work is surely mathematics, although Bravais apparently never had a position in mathematics department. Another example is Kekule. Many of you certainly know about this. You have studied in chemistry, that he discovered the ring structure for the benzene molecule. Benzene molecule is C6H6, 6 carbon atoms and 6 hydrogen atoms. Now, this was the first molecule whose atomic picture, so they used to draw pictures, putting atoms at the nodes and the bonds, etc. But the Kekule's work is in 1865. Before that, the atomic theory was just developing. And the previous molecules they came across, they always were planar trees. On a tree, you could, tree in the mathematical sense, a graph in graph theoretic sense, nodes and edges where there is no cycle. But this ring structure, this is the first molecule they came across, which could not be structured. This is a very confusing point, how to put this C6H6 on paper. The difficulty was, this was of cycle rank 1. This was a graph with cycle rank 1. So, I would say that what Kekule did was mathematics. Still another example, Paul Samuelson. I do not know whether you have courses in economics at IISER. He was the first Nobel laureate in economics around 1950s. And he wrote his famous Foundations of Economic Analysis. Nobody had used the word foundations before Samuelson about economics. So, he says foundations of economic analysis. The story is that as an undergraduate, he was at Yale, and at Yale there was this person, Josiah Willard Gibbs. He was a really mathematician, but interested in thermodynamics. And Samuelson had an exposure to these ideas when he was an undergraduate. Now he comes to the graduate school and at MIT at that time, and he wants to develop this economics. So he has these thermodynamic ideas, and this is how he formulated his foundations of economic analysis. And in the preface of that book, he gives a very special quote by Gibbs, that mathematics is the language, correct language. This is like Galileo. Now, these thermodynamic ideas, these are expressed in physics as thermodynamics, but this is really calculus of variations, or Morse theory in differential topology. So, these examples illustrate considerable extension of giving meaning to the ontological idea of space in the definition of mathematics given above, which goes beyond, much beyond Newton's beginning ontological idea of space, meaning Euclidean three-dimensional space. In mathematics itself, there are many examples: the idea of a Riemann surface, the idea of a Riemannian metric, the idea of a manifold equipped with various set theoretic structures like symplectic structures, contact structures, etc., which extended the meaning of the word space. So, with this equipment, let us muse about the much debated philosophical question about mathematics: is it objective or subjective? In a more colorful language, the question is mathematics a discovery, like discovering some pearls at the bottom of a sea? They are different from you. They are there and you are discovering them. Or is it an invention brought out by the human mind? These are philosophical questions discussed for centuries. And Dedekind was already writing on this. I think he clearly had that this debate in his mind. He had already expressed clearly his opinion in a very significant case: real numbers are creations of the human mind. I leave it to you to form your own judgment on this issue. Previously, some great minds, without again defining what mathematics is, had expressed their thoughts about mathematics in the following words. Bhaskaracharya says, 12th century, mathematics is the eyes of the Veda Purusha. He is thinking in terms of creating a theory out of Veda, and is describing Vedanga, and there were traditionally 6 Vedangas. Grammar is one of them. So he says that Shabda Shastram Mukham, the grammar is the mouth of this Veda Purusha, and Jyotisham Chakshushi, Jyotish means mathematics here, that mathematics are the eyes of the Veda Purusha with which to see the world. Now, Galileo had expressed the book of natural philosophy. They use the word natural philosophy. This is before Newton, and that was at that time the physics and chemistry. These words were not there. So he was using the word. The book of natural philosophy is written in the language of mathematics. Galileo uniformly avoids the word God everywhere here. Its characters are triangles, circles, and other geometric figures. What does he have in mind? Other geometric figures? He had Kepler's laws of motion before him. So he was saying, these ellipses, and these are the geometric figures. And in terms of those, his ideas are to be expressed. And the original passage is really worth reading. I leave it to you. And let's come back to Einstein again. In some other ways, he would say also this: imagination is more important than knowledge. Here he is using the word knowledge means some data collection. He says imagination is more important than knowledge. for knowledge is limited, imagination encircles the world. Except that being a physicist, without bothering to define mathematics, he had forgotten to insert a few words in this sentence. Imagination of whose? Imagination of the mathematical mind, giving a meaning to the ontological words or statements in the thought categories of number and space, is more important than data collection of knowledge. Thank you.